Hi everyone, I'm going to be talking about our paper, A Scale-Invariant Sorting Criterion to Find a Causal Order in Additive Noise Models. This is joint work with my co-authors Miriam Tami, Christoph Seiler, Anton Schambas, and Sebastian Weichhold. You can find implementations relating to our paper under causaldisco.github.io/causaldisco. We'll be talking about additive noise models, which make a convenient functional assumption for causal discovery and observational data. Normally, causal discovery often requires interventional data. And we consider linear additive noise models of this form between random variables x, a weighted adjacency matrix W, and a vector of independent random variables n, which represent the causal noise. The problem of additive noise models is, despite their favorable properties, there's few real-world ANMs which are known with high confidence. So most causal discovery algorithms are evaluated on synthetic data from simulated ANMs. And these simulations may not be realistic, or at least we wouldn't know whether they are. This is why having a close look at the data being generated from these ANMs for simulations is a good idea. And what we find is that there's a hidden pattern in ANM data concerning the R-squared, the coefficient of determination. Consider, for example, a causal chain of length P, where noise variances are sampled IID and weights are also sampled IID from distribution PW. We prove that the coefficient of determination R-squared given all other variables converges to 1 as P goes to infinity under the following condition. The condition basically says that the weights are sufficiently high such that the expectation of the log of the weights, of the absolute value of the weights, is greater than 0. This implies that causal chains meeting this condition become increasingly deterministic along the causal order. You can imagine a random variable that's completely determined by the other random variables has very little or vanishingly little noise contribution. And we can exploit this pattern to find a candidate causal order, which is very useful for causal discovery. So far, this is just on chains, but the same pattern occurs in many other ANMs. We introduced the idea of R-square sortability, which measures the agreement between an ordering by R-square and a causal order. A value of 0.5 amounts to random ordering. A value of 1 amounts to perfect causal ordering. When simulating different additive noise models and data from it, then we find that for a varying number of nodes and other settings, the R-square sortability tends to be well above the 0.5, which would be a random ordering. So sorting by R-square tends to give very good proxies of the actual causal order. And this includes settings where the weights are far from extreme. The impact of the R-square pattern on causal discovery is quite remarkable. We measure it by introducing the baseline algorithm R-square sort and regress, which sorts by increasing R-square and then regresses each variable onto its predecessors in this order. When simulating different ANMs and data from them and ranking them by R-square sortability, we find that the performance of R-square sort and regress gets better the higher R-square sortability is. And most importantly, from about 0.7 onwards, we see that R-square sort and regress can rival the performances of established structural learning algorithms such as PC and FGS. And as we've just seen before, such high R-square sortabilities are not rare at all. And the advantage of R-square compared to other baselines is that it is scale invariant and thus unaffected by arbitrary data scales, which are common in real-world data, or rescaling, which includes standardization, which is a common pre-processing step. In summary, we find that regarding ANMs, many of them have increasing R-square along the causal order, and thus can become increasingly deterministic with more variables. This opens up the question, do we find similar R-square patterns in real-world data? And depending on that, how should we best simulate ANMs? As for causal discovery, R-square sort and regress is a competitive baseline. In the context of R-square sortability matters for the interpretation of performances. Now, you might go and ask yourself, how good is your favorite algorithm compared to R-square sort and regress? And perhaps are there other algorithms that exploit R-square sortability, ones that we can design intentionally, or perhaps ones that already exist and we just didn't know that that's what they did? You can see for yourself by trying out the R-square sort and regress baseline and measuring the R-square sortability of your own data with our library causaldisco.github.io/causaldisco. Thank you.